I'm Jonathan Charnes. I'd like to thank you for watching my video, part 2 of the UPS Flight 2976 NTSB preliminary report, and the information that I should say the NTSB deliberately left out. I calculated this, and from what I've calculated, I'm pretty sure they could have set the plane down in the remaining stopping distance that was available. It would make my work a lot easier if the FAA provided simple information like what was their rotation speed, where were they on the runway when that happened, but I'll have to derive all this forensically. First thing I'm going to do is use some of the NTSB's information. They said they had the first bell at 37 seconds. Well, they said the takeoff was normal until they rotated. Then they heard the bell. This most likely is when the first engine fell off. If we look at this graph, this is from Flight Radar 24. The yellow shows the airspeed, the blue shows the altitude, the times are written down here. From this information, I can start using some calculations. I made a copy of the graph up here, which is a little easier to see. I did it freehand, but it's not to scale. But it showed that they basically started the takeoff roll with a speed of 8 knots, and then they ended up at 187 knots, and their time frame was, I think, something like 27 seconds, which doesn't really agree with what the NTSB says. They also had a peak altitude of about 175 feet. Well, the NTSB says the highest altitude was maybe 50 feet, something like that. So some of this information is incorrect, but some of it we can still use, because at this point where they reach their peak airspeed and stop acceleration, that point must be where the first engine fell off and when they heard the bell. Now they continue at the same altitude, at the same airspeed, but they're still continuing a climb. This is just after rotation, and about 10 seconds later, the climb stops and they start a descent. Well, that most likely is because the second engine lost most of its power at that time. If you recall, when the first engine fell off, there was a lot of fire because the fuel line broke, and you're getting minimum 10 pounds per second fuel flow being pumped out, probably several times that, because the pumps have to supply more than what the engine would use. So all that burning fuel, I'm sure, acted like a fire extinguisher and went to the center engine and caused flame outs or compressor stalls. And so now the plane is coming back down, still maintaining its airspeed. Flight Radar 24 shows that it maintained just about the same speed until impact. But some things don't add up, like Flight Radar, if we look at their acceleration time to when data stops, it's like 83 seconds. Well, the NTSB said it was 37 seconds to the bell and then 25 seconds after that to impact stop, so that's like 62 seconds. So I'm more inclined to believe what the NTSB says than Flight Radar 24, although these points are significant and they can't really be ignored. So anyway, getting back to this, what happened where in the runway? Well, the first 846 feet were not used. They did an intersection departure because the taxiway doesn't lead them to the end of the runway, so rather than back taxi and waste a few minutes back taxiing, tying up the runway, turning around, they took off with the intersection, and under normal circumstances, no problem, plenty of runway. Anyway, how much distance was required to accelerate? Well, that would be initial plus final velocity divided by 2. It's average velocity. And then if we multiply that by time, which was 37 seconds, you get the distance covered. Here's my initial velocity in feet per second, which corresponds to 8 knots. 312 feet per second corresponds to 187 knots. I forgot to show you that I divided by 2 here, but I did. This is 6,013 feet. Now, the next thing is, when did the second engine fail? Well, that's when they lost their ability to climb. We know that the plane stayed in the air on one engine for about 25 seconds. Wasn't able to accelerate, wasn't able to climb, but that's the power it basically needs just to stay in the air at its current weight. One engine power or thrust of 60,000 pounds. So when it's climbing, it has about 60,000 pounds to provide it in the climb, and I will go over how I obtained the rate of climb in a second. Yeah, I have it here. The rate of climb on 2 engines, so there are 2 engines operating, it's 2 engine thrust minus the thrust required to maintain altitude and constant airspeed. Well, that's about 60,000 pounds. 2 engine thrust is 120. So 120,000 pounds minus 60,000 leaves us 60. Now if we divide that by the weight of the airplane, that gives us basically the slope or the angle that it could climb at. And that's a gradient of 120,000 over 630. If I multiply that by the speed, 312 feet per second, which is 187 knots, I get 30 feet per second that it can climb at. Now, knowing it's climbing at 30 feet per second, and if I know the height that it climbed to, say 50 feet, some might say 60, it's close to that, but 50 divided by 30 would be 5/3 of a second. So the time it takes, we see, is 5/3 of a second to climb 50 feet. So in other words, just a little bit after the first engine failed, almost 2 seconds, a little less than that, the second engine starts to fail. If you look at this graph, it suggests about 10 seconds. But in 10 seconds, the plane should have been 300 feet above the ground. And that never happened, so that's why I'm more inclined to believe it failed about 5/3 of a second, maybe 2 seconds after first engine quit. In any case, how much distance is that? Would it cover? Okay, well, we have distance is speed times time. So this doesn't look right. The distance it took to climb, yes, to 50 feet. All right, so it's not 50 feet is equal to this. It's how much runway it uses. So 312 is the speed times 5/3 of a second to be 520 feet. Okay, so from first engine failure to second engine failure is 520 feet. And if we can see that, let me turn this around a little bit. Yeah. Okay. So again, 846 feet they don't use, 6013 to accelerate to 187. 520 feet to the second engine failure. And now let's give them 5 seconds to react and put the plane back down on the ground. 5 seconds at 317 feet per second would be 1560 feet. Okay. Well, so I had this covered. It's reaction distance, speed times time, 312 times 5 is 1560. Sum of all these distances so far, 8139 feet. Now at the end of the runway, there's a 400-foot overrun, roughly. It remains. This is the usable runway or allowable runway, 11887. If I add the 400 hard surface to overrun and subtract this from the distance they used, so they used 8139. This is what the total length of the runway is, and the difference would be 48 feet to stop. Okay, now braking depends on the coefficient of friction and our speed that we start braking at. Coefficients of friction can vary on dry surfaces between rubber and concrete. It can be anywhere between 0.3 and 0.5. I picked 0.4, which is in the middle. However, we only have 10 out of 12 wheels with brakes, so that would reduce our total coefficient a little bit. I multiply this by the acceleration of gravity. I now have my acceleration that it'll stop. It's negative because speed will be reduced. So 0.4 times 10 twelfths times minus 32 is minus 10.7 feet per second squared. Here's the formula for distance. And if we do all this arithmetic, 1/2 at squared plus initial velocity times time, you run this through, and we wind up getting 4725 feet are required to stop. Well, that's about 600 feet short of more than what we have. However, there's an overrun, there's grass beyond the overrun of about 700 some feet, which can be used to stop the plane. Anyway, let me think a second. Oh yeah. Yeah, to get the time, forgot to tell you, time is change in velocity divided by acceleration. So we start out at 317, and we want to end up at 0. So change in time is final minus initial, so 0 minus 317 is 317. Divide that by the acceleration, it's 29.7 seconds to stop the plane. So that's how we arrive at the 4725. Hope that's a little bit more clear. 29.7 times 29.7 is about 883. So that's 1/2 at squared, initial velocity times time. Here's initial velocity again, here's the time. This is positive, but this part's negative. So you can do the arithmetic, it's no big deal, as you see. Again, we're 577 feet short. All right. So if we do this, I want to know how fast I'm going when I run out of hard surface. Well, final velocity is the square root of initial velocity squared plus twice the acceleration times distance. Here's our initial velocity squared, which is 187 knots, 2 times our acceleration is negative, times the distance, 48 feet. So you multiply all this out, take the square root, it's 92.6 feet per second, which is about 57 knots, something like that. So how long will it take to stop this if we have grass? And the coefficient of friction on grass is less than what would be on concrete. There's many different coefficients of friction depending on what type of grass you have. So again, I'm going to say it's definitely less than the 10.2. I think negative 0.7 might be reasonable. Using this, and again, it could be off. And it can vary. As long as the grass is dry, it should be something like this. But then you also have to worry about the dirt underneath the grass not failing. So it depends upon the tire pressure, and these are higher pressure tires. So this part, there might be a little error in here. But getting back to this, time is change in velocity divided by acceleration. So here's the velocity change. Here's our acceleration. So it'll be about 13.2 seconds to stop. Distance, average velocity, which is initial plus final divided by 2 times the time, about 612 feet. So yeah, that suggests they would be able to stop before they hit the building. If we look down here, I kind of drew all the distances. The 846 that they didn't use, 6013 to accelerate, 520 between engine failures, 1560 to react. Here's the end of our hard surface. Over here, here the hard surface ends. 700 feet or so beyond that is the building whose roof they hit. And then they crashed about 1136 feet after that. How do we know that? Well, from the point of rotation, we have about 25 seconds according to the NTSB. So 312 feet per second times 25 would be 7,800 feet. So this is where the data ended. The final wreckage was about another 1,000 feet beyond that. They say 3,000 feet beyond the building was where the wreckage wound up. But of course it took impact to start slowing it down, and that impact most likely stopped the data. So that kind of verifies that it all adds up with these numbers, basically. If we look at this, 14,659 feet from the beginning of the runway to where the data ends. Oops, I should have drawn this arrow back here. It's here. If you go to Google Maps and look at this auto parts place where they say it ended, and start from the beginning of the runway, you'll have a similar distance. So it kind of verifies it. Another verification would be to look at the airport diagram. Here's the airport diagram. Now, I spent a lot of time measuring distances on this with a vernier caliper, and I've also looked at the NTSB photos, and the second one that shows the engine falling off shows a hangar with a whitish doors and a bluish roof in the background, which is somewhere over here. It's most likely this hangar. You can't see any buildings beyond that, so that's why I doubt if it's this one. And also, if I put the plane's position over here, that's at 6,542 feet. Well, my calculation so about 6,800. So maybe it got off a little sooner, but the NTSB, if they wanted to, can tell us exactly where that happened. But We know it's somewhere, has to be here, because 6542 is pretty close to what I calculated. And again, this could be a little off depending upon which you choose, what point. Well, knowing those points are important. They showed me that they should have been able to stop, or just about stop, before they hit the building. But training just teaches them for one engine out, and you're told basically when you reach takeoff decision speed, which is V1, you continue flying unless something really extraordinary happens, which it did. But to recognize and do something in a reasonable time, it's very difficult when you don't have any training to deal with a double engine failure with one engine remaining. And on top of that, the FAA has two definitions for V1, for takeoff decision. One would be the minimum speed that one engine can fail and you can continue the takeoff. I've kind of come up with a little example of a jet. And in that case, if we had about a 9,500 foot runway or 9,950 foot runway, at 120 knots, if we have an engine failure here, so it would take about 2,500 feet to accelerate to 120 knots. And then the plane could continue to accelerate to the rotation speed, and it could climb and clear an obstruction. And so it would require about 9,900 feet of runway if they rotated at the speed as low as 120. If it happened at a speed less than that, then they wouldn't be able to do this. So that's one definition of V1, which would be, again, the minimum speed an engine can fail, you continue takeoff. But another one is the maximum speed you can accelerate to and stop on runway available. And that depends on the braking condition of the runway. In this example, they should be able to accelerate to 168 knots and then stop and have enough runway to stop. But now let's look what happens. You reach 120 knots and you're committed to take off. And now let's say you have an engine failure. Well, that doesn't mean you have to continue flying, but yet pilots are brainwashed into continue flying once you're at V1. It depends which definition of V1 you use, because if it's based on accelerating and stopping, they could be as high as 168 in this example and still have enough distance to stop. But a lot of the air carriers simply use the slower V1, and they'll continue flying, and probably 99 times out of 100 that's the best choice. But in exceptional circumstances or extraordinary circumstances such as this, you need simulator training dealing specifically with a dual engine failure if you have a 3-engine aircraft. And that's not provided. They need to know, can this plane climb on one engine? And obviously it couldn't. So now the question is, well, why do you allow the plane to fly at a weight which will not permit it to clear obstructions with a dual engine failure? If it was 100,000 pounds lighter, if it was like 530,000 pounds instead of 630,000, they probably have made it. But the regulations only require them to plan for one engine failure, because 2-engine failures are so rare. But, and again, could they have survived by recognizing that, hey, we aren't climbing, we aren't going to try to set it down, why not raise the landing gear? That would probably give it another 200 feet a minute rate of climb, something like that, once the gear's up. The only other problem is that the gear doors open. That adds drag, so that will tend to slow the plane up a little bit for 10 seconds, because that's about what it takes to retract the gear. And nobody's trained to do that. Nobody knows how that's going to affect the performance. That information should be readily available to pilots, and it's not. We can do this probably in a simulator to see what the rate of climb, if that would improve with raising the gear. Best to do it in the actual airplane at altitude, so if you do lose a bit of altitude, you don't hit the ground with the gear up. But so again, I don't see how the city of Louisville or the FAA could permit them to have buildings within 700 feet of the end of the runway. That's unsafe. You know, a lot of the area around that is pretty sparse or empty for the most part. Well, why not forbid any buildings along the runway line with maybe 500 feet right or left of it, and then put them all in the in the low density occupied spaces to the right and left of that. A lot of airports are safe, like Rockford, a lot of empty fields at the end of runway 19 there. So although it has a shorter runway, there's more empty space to go into. So anyway, yeah, here's the definition, the FAA's definition of V1 over here that I talked to you about. The Canadians have a different definition of V1. So if you're interested in that, fine. Thank you for watching.